Okay, so back in algebra, you learned a number of different properties that you used when you were solving equations. And we're just going to review those real quick, and then we'll take a look at how these properties can help us do proofs in geometry. So the first four are named after the basic operations in math: addition, subtraction, multiplication, and division. And I'm going to write out what the way they're described in most textbooks, but you're going to remember these as like I always taught them as you can do the same thing to both sides properties. So like for instance, addition is you can add the same thing to both sides property. Now the way it's explained here is it says if A equals B and C equals D, then A plus C will still equal B plus D. So whereas I had A equaling B, if I added two things that were equal to each other, right, I added C to one side and D to the other, but right here it shows me that those are equal, I still have a true equation. So that's basically the you can add the same thing to both sides property. Subtraction property is the you can subtract the same thing from both sides. So it's just like the one above, only we change the addition to subtraction. So if A equals B and C equals D, then A minus C equals B minus D. Multiplication is the idea here is that we can multiply. If I have A equals B, then I can take the A and multiply it times C, take the B and multiply it times the same thing, and I still have a true equation. Division property is that so long as I'm not going to divide by 0, then if A equals B, I can divide it by C, and I can divide B by C, and again, as long as C is not a 0, then I have a true equation here. Substitution property, this one's a little bit different. Now we're moving on to not the you can do the same thing to both sides properties. This is the idea that if A is equal to B, if these two things are equal, then they're basically interchangeable in any equation. Then either A or B may be substituted for the other in any equation. Right? So this is the idea that when two things are equal, you can take one out, put the other in, and you still have a true equation. Now the reflexive property we didn't use too much in algebra. It just says that everything is equal to itself. A equals A, where A could be anything, so everything is equal to itself. The symmetric property says if A equals B, then B equals A. The idea here is that the left side of an equation and the right side of an equation, they can be switched for one another, and you still have a true equation. Now the transitive property is something that's pretty useful. It's almost like a shortcut, I think of it. It says if A equals B and B is equal to C, then, well, actually we can kind of think about this as almost like a substitution. Because if A is equal to B, then I can substitute A for B in any equation. So I can come, right, these are interchangeable based on what it says right here with the substitution property. So when I come to where it says B equals C, I can change that B into an A, right? So if A equals B and B equals C, then A equals C. In a way, it's a lot like the substitution property, but we call it the transitive property. We just say that since both A and C are equal to B, they are equal to each other. Now, where did we use those properties in algebra? We used those when we were solving equations, right? These were the basic ideas behind the steps that we took when we were solving equations, subtracting the same thing from both sides and dividing dividing both sides by the same thing. That was the idea the basic idea behind solving equations back in algebra. But now we're going to take a look at how we can use these in a proof, and as well as some other ones, in a proof in geometry. First of all, I want you to notice that when we were talking about all of these, it was all dealing with equal signs. And in geometry, we have another sign that we use a lot, right? The congruence sign. So in geometry, we use this idea that even though the distance between D and E is equal to the distance between F and G, if those were actual segments, if there was a segment DE and a segment FG, we could say that segment DE is congruent to segment FG. And it doesn't technically mean the same thing as this statement right here, but we use them interchangeably a lot in our proofs in geometry, right? They don't technically mean the same thing, but in a proof, they're basically the same thing. And the same goes with angles. So if the measure of one angle is equal to the measure of the other angle, in this case, measure of angle G is equal to measure of angle E, we can say that angle G is congruent to angle E, and those statements can be used interchangeably. And so what that means is we have the reflexive property of congruence, where everything is congruent to itself. All segments are congruent to themselves. All angles are congruent to themselves. We have the symmetric property of congruence that says that when we make a congruent statement saying that two segments or angles are congruent, it doesn't matter what we list first. So if we said that segment DE is congruent to segment FG, we can turn that around and say that segment FG is congruent to segment DE. Those two statements are equivalent. Or if angle D is congruent to angle E, we can say that angle E is congruent to angle D. We can put either angle first in that statement, and it's an equivalent statement. Transitive property, so kind of like what we talked about in the transitive property of equality, if D is congruent to FG, but FG is congruent to JK, then that would indicate that DE is congruent to JK, because both of these things are congruent to segment FG, so they must be congruent to each other. And the same thing will happen with angles. If angle D is congruent to angle E, and angle F is also congruent to angle E, then we know that angle D has to be congruent to angle F. So let's take a look at how some of these properties work, how we use them when we were solving equations, right? I told you on the previous page that we used these properties to solve equations. Well, here we have an equation. Let's show how we use those properties to solve this, right? You know what these steps are. If I gave you this equation, most of you would have no problem solving it. In geometry, though, we're not so much concerned about how we do a problem. We're concerned with what allows us to do the steps that we do to solve the problem, what justifies each step. So that's what we're going to kind of explain here. Now, step one, if you were actually doing this problem, step one would be you'd probably just write the problem out, right? In geometry, we call that the given information. So the reason why you could start your solving process by writing this problem is because that information was given to you. Now the next thing we do is you can notice that the 3y turned into a 15y, and the 4 turned into a 20, and the 2y over 5 just turned into 2y. Well, how did all that happen? How did this change? How did step 1 change into step 2? Well, we took everything in that first equation and we multiplied it by 5. And so that is called the multiplication property, the property that says we can multiply both sides of an equation by the same thing. Multiplication property. Technically, it's the multiplication property of equality. Then from step 2 to step 3, what you'll notice is the 15y turned into a 3y, or I'm sorry, a 13y. The 20s didn't change, and 2y became nothing. So how did that happen? Well, we took 2y away from this side, and we took 2y away from the 15y. So we subtracted the same thing from both sides. So the reason that justifies step 3 is the subtraction property, the property that says you can subtract the same thing from both sides. Technically, it is the, not congruence, it's the subtraction property of equality. Then we did the same thing again on step 4, right? We subtracted 20 from both sides so that the 20 went away from the left side of the equation. So again, we used the subtraction property of equality. And lastly, we turned in step 5, we turned 13y into plain old y, and negative 20 became negative 20 over 13. How did we do that? We divided both sides by 13. So that's the division property of equality. Division property of equality. So example 1, it says, could be described as a proof of what biconditional. Remember, a biconditional is that statement that says P is true if and only if Q is true. And so this statement, what we just did is we said that 3y plus 4 equals 2y divided by 5 if and only if x is equal to negative 20 over 13. Now, many proofs in geometry are going to follow a similar pattern to what we just did. You're going to be given a diagram and some information about that diagram. Now, we didn't necessarily have a diagram in that previous one, but we had some certain information that we knew is true. Our job in a proof is then to take that information that we're given, or that diagram that we're given, and use other things like theorems or postulates or definitions of certain things in geometry, like definition of a midpoint or definition of a right angle. And then through the use of those different kind of tools that we have, we can prove that based on a certain given information or a given diagram, some other statement must be true. Now, when we do proofs in this class, most of them will be two-column proofs. That means that they're going to have, well, two columns. One side, you can see here, is going to be a number of different statements. And then for each statement, we have a reason for why it must be true. So statements on the left and reasons on the right. So let's look at example 2. It says, given that segment RT and segment PQ intersect at S. So let's just do a quick sketch of segment RT and segment SQ intersecting at S. Intersecting at S. I'll just kind of, doesn't have to be perfect. All right, so there's segment RT right here, and segment PQ. Now that's intersecting at S. So that point there is S. And it says such that RS is congruent to PS. Now I didn't draw because when I was sketching this out, I didn't know what was going to be congruent to what. So these aren't actually drawn congruent, but that's okay. They don't have to be drawn to scale. These markings are going to tell me that even though it doesn't look like PS is congruent to RS, they are congruent to each other. And secondly, we know that ST is congruent to SQ, right? Now our job is prove that from R to T is equal to the distance from P to Q. Or another way is to think, well, how does this information tell us that segment RT must be congruent to segment PQ? So when we're doing a two-column proof, the first statement that we make is almost always the given information. So our given information is that RS is equal to PS and ST is equal to SQ. So we stated that there. Now we said that RS plus ST is equal to PS plus SQ. Well, let's take a look at what we have here. We have, if I were to kind of color code these two things in this statement, we have RS and PS. And then if I were to color code these two things, you see they show up added to the two distances that we already knew were equal. So what's happened here is we've taken this equation, RS equals PS, and we've added the same thing to both sides. It doesn't look like the same thing. It looks like we added ST to one side and SQ, but we know that those two things are equal to each other. So I've added the same thing to both sides of this first equation. So what does that mean? That means I used the addition postulate, or the addition property, I should say, the addition property of equality. Then I come down to this next statement. It says that RS plus ST, and it might not be real clear where this is coming from at first until I notice that on my picture, RS is kind of the left part of segment RT, ST is the right part, and it's this statement, this equation right here, is saying that if I add RS to ST, I get RT. And that should ring some bells to you guys. That is called the segment addition postulate. And if I notice there's two parts to statement 3, the second part of it is just basically saying the same thing about segment PQ, that if I add PS to SQ, I get PQ. So this statement right here is justified, saying that these two things add up to equal this one, and that these two things add up to equal that one. That is justified by the segment addition postulate. And we abbreviate a lot when we do these proofs, so hopefully you understand this abbreviation, segment addition postulate. That justifies that those two equations must be true. So now we come to statement 4, we say, okay, well, how does all of that lead us to conclude that RT must be equal to PQ? I'm going to do a little color coding again. Here's RT. Where else do I see RT? I see it right here. Okay. Here's PQ. Where else do I see PQ? I see it right there. Now, why could I say that those two things are equal? Because take a look. RT, it says, can be turned into this. Or, I guess you could think of another way, this could be turned into an RT. And this, let's go with this color. This right here could be turned into PQ because those two things are equal to each other. Now, if we come up here, we see in step 2 that PS is right here. PS plus SQ is right here. And RS plus ST shows up right here. So those two things that are equal in step 2, we can turn the RS plus ST into the RT. So you can see we took that and turned it into RT right there. PS plus SQ can be substituted with PQ, and that's what we did. We turned PS plus SQ into PQ right there. So what we did is we took statement 2 and we substituted the left half of statement 2 with RT. And we substituted the right half of statement 2 with PQ. Because in statement 3, we said that the left half right here is equal to RT, and this right half is equal to PQ. So we took statement 2 and we substituted two different things in, one for the left side and one for the right side. So that means what we used here is the substitution property. And that is a basic proof. Now I know right now it might not feel very basic because this is the first time you've kind of encountered a proof, but it's going to get a little bit easier. I promise you this, right? We start with our given information, and then we use theorems and postulates and definitions that we've learned to kind of build off of that statement and see what else can we prove is true. Now there's a couple more examples on your notes. We're going to actually take a look at these in class. If you want to give these a shot, I'm going to post a video of me completing example 3 and example 4, and you can take a look at that. But as of right now, I think this is going to do it for this video. Hopefully now you have a little bit of an idea of how we do a proof, the basic ideas behind doing a proof, a little refresher on some of these properties that we learned back in algebra, and I'll see you next time.